Go. So do you remember what this fundamental theorem calculus was in calculus 1? We had two actually, part 1 and part 2, and your favorite one, recall, your favorite one was the one we're using every day, literally right now. Integral from a to b, when you have a derivative inside of the integral, the derivative of f. To calculate this integral, you find antiderivative, which is f, right? Plug the top minus the bottom. So it's literally what we're using every day. And sometimes in the notes, they're using capital F. So a small f used here, the x, and then they use capital F, b, minus capital F, a. This book uses this notation, where f is called antiderivative, первообразное, antiderivative, yes, from a to b. So that's literally the most important part. I mention it in my classes when I teach. There are several things in mathematics that change the world forever and deserves Nobel Prize. We don't give Nobel Prizes for math majors, for you to know. So yeah, there is the gossip that Nobel caught his wife cheating with a mathematician. Or maybe she just fell in love with a mathematician, and since then he excluded math majors, the only major excluded from Nobel Prize. So we had our own one.
Wow, there goes my hopes and dreams.
Yeah, so that's interesting. Some mathematicians are faking to be statisticians or something like that to get Nobel Prize.
Oh.
They just rename themselves to be not mathematicians anymore. That's interesting.
So does that mean I can get a Nobel Prize?
You can, you can figure it out. Ion, you'll figure it out.
You need to know about peace prize.
So, what I wanted to say is there are several things in mathematics that deserves Nobel Prize or being recognized forever and forever. And this short formula is one of them. This idea that we have antiderivative of x squared is x cubed over 3, and then somehow it got connected with areas, that is insane. Like the undoing derivative, which is coming from velocity to distance, and then somehow it became area below the graph. This equal sign changed mathematics as it's ever been before. So that's a genius idea, beautiful and short genius idea. And that's why it's pretty cool that some genius ideas are actually very short notational. So how to do the same thing, but above the line. Remember, this is kind of representation, the area below the graph, and lots of other things, right? But we are now talking about the line integrals. So line integral is a different thing. Line integral has like a 3D shape, and then above the line, right? And then you connect these two, and it becomes a fence. So 3D shape is not the same thing as 2D shape. So how to figure out the same thing, but for line integrals? And the formula looks like so, very elegant formula. Over C, you remember that. C is this one on the floor in 2D. Then we have your familiar notation times dr. The idea is still the same. We're gonna plug the top minus the bottom, but in this case there is no top and bottom. There is end minus start, and that's a pretty cool idea as well. So if we're starting from this, which let's call R of A, and we're going to direction matters, we're going to R at B, then it will be find F. So undo differentiation, find F, plug the R at the end point, minus, guess what, plug the right point, the beginning. So instead of top minus bottom, we always do big minus small. That's the idea. R at A. So it's always big, or in this case, end minus start. Yes?
I'm guessing that is
the formula.
Yeah, is the first delta F, is that the gradient or no? I'm assuming not.
Those are derivatives, that's why we're undoing them. So the idea is going to be the same, yeah. You will see right now how we're going to do it. It's going to be interesting. It's a little bit more complicated than just undoing the derivative, but technically speaking, it's undoing the derivative. Yeah, you will see. And don't forget delta is this, and then this one is del, but it's fine. You slowly get used to it. So del and delta, that's not the same thing. Yeah.
Good name.
Now, right? Yeah. So creative. Now let's do it. So basically, we say integral over derivative is right-hand side. We're integrating the derivative. This is the collection of derivatives. So we kind of figure this out. There's a proof of this if you want to check the proof. But let's do the example. Example 1. Example should make it look better. Find the integral of CF dr where f x comma y equals xy squared comma x squared y, and C is any curve from, and C is, and that is a very interesting idea. What does it mean to have any curve? So that will be pretty creative from now on to work with different parameterizations and curves. Any curve from 1, 2 and 3, 4. So let me keep it for you. This is going to be a genius idea again. Why? Because as you remember, it's not also, you need to connect several ideas. Just like with the integral, area below the graph was like the weirdest dumb explanation of the integral. Integral is so much more than that. Integral is a accumulation of different speeds at the same time. If integral is a accumulation of changes. What kind of velocity was at this moment, this moment, this one? I was speeding, I was slowing down, there was a stop. All this accumulation is integral. Integral gives me distance from velocity. How amazing is that? So area below the graph was like the weirdest way to explain it for the very beginners. Same with the line integral. Yes, we gave you this integral and we told you, oh, it accumulates something above the curve. But then I introduced you to this amazing idea of going through the vector field. This is the integral that calculates what is happening when you are moving through the rain and the rain is pulling you sides or not, how much water you'll get with respect to the rain being behind you, side you, in front of you. The wind is blowing in the car and you're driving. How strong the wind matters, what direction of the wind matters. Collecting all these little arrows on the way of dr. Drs are the speeds. F is your force. For example, the vector field like wind, I just said. So F is your wind and C is you driving over this highway during this wind. How it's pulling you aside or not, maybe it's helping you because it's from the back. So this is all genius, how we collected this all into one convenient integral notation. And now let's just learn how to do that. Sketch the graph first. Solution. Always start with a nice looking graph. In this case, it's just from a graph of 2D. Let's do it like this. We don't know how the curve looks like. It says any curve from 1, 2 to 3, 4. Okay, any, and then I don't know, just randomly, just choose some. C has direction, and we're gonna figure out the function r of t to describe it. So then, that's interesting, what is happening here. We actually mentioned in the previous chapters something about conservative vector fields and so on. And this was the idea that for any, that's a question. Well, okay, that's fine. For any f, we can find, we can find small f such that, such that f are collections of derivative of the small f. So no, that's a question mark. No, as you remember, the field should be conservative. Only if f is conservative. This word will be more clear on Wednesday. I will explain you more. But conservative fields are basically nice fields you want to work with. We have to figure out what does it mean to be conservative. You will hear this term a lot in physics. What does it mean to have conservative magnetic fields? Did you hear already? They kind of mention sometimes conservative magnetic fields, conservative electromagnetic fields. So they will explain it to you from physics point of view, and we're going to explain it from a mathematical point of view, and both will be using a formula for that. We both use a formula in math and physics. So what we're doing here is, if F is conservative, then you can find this small f, make this equal sign. Then when you find it, right, and you build this integral over c with f inside and dr, and this will be easy to evaluate. And that's the whole idea. Evaluate. Conservative fields are good because they build an easy line integral, so it will be easier to accumulate all the magnetic forces and so on. So for this particular example, we have f x comma y equals, it is given, let me go back. Oh, it is not. This one, capital F is given. So we have capital F. Capital F is given, let me scroll up. And you guys guess, what kind of function, not a vector, a function, could give me this when you differentiate it? That's actually a pretty creative process here. Close. What did you say? Let me write down. So we have f. Then let's find. How would I explain it? Then I want to explain it. We're making this. So we find, like we guess. Okay. We find a small f that will give you this when you differentiate it of x comma y, so it's two-dimensional, and it's going to be a function, not a vector. Guess.
X squared, y squared over 2.
Ah, so smart. X squared, y squared over 2. Let's check. So smart. Look at that. Look at that. So smart. You differentiate with respect to x. It will give you 2. So f prime with respect to x. 2 goes down, cancels 1/2 x, and then y squared matches. This is exactly what we need here. F prime with respect to x. F prime with respect to y is 1/2 times 2, but now it's going to be x squared survives and y at the end matches. This is, so it's a creative thing. Definitely, I would not even say we do integration here. It's kind of like you need to try different things and adjust it a little bit. Like with this 1/2, you had to adjust it because there is no 1/2 in your function, and so on. So that's pretty cool. So I would say because BC, because, right? Like so. Finally, let's finish the integral. That's kind of the most important part. Then they ask us to find integral over c f dr, which is integral over c. That's the most important part. Here is this formula we just learned. Find this function, small function f, which is antiderivative kind of the vector field f, capital F, and multiplied by dr. That is a new formula we just learned right now from the box above. That is going to be, let me make it in green. In green, it will be a function from the end minus a function from the start, like so. So let's continue. The end is near.
Yes.
And the class is almost over. Just a second. This is my end. So f of 3, 4, and then 1 and 2 is the beginning, right? So f 3, 4 minus f of 1, 2, right? That's the idea, we know it. And now we don't even integrate anything. That is a genius idea. Just like we did in Calculus 1 class, let me go back to explain you. We did what? The moment you calculate antiderivative, you're done. If it's x cubed over 3, you just plug the top minus the bottom, you're done. Same here. We found antiderivative, which was kind of complicated. You have to think a little bit, try different things. It doesn't work, it works, and so on. But the moment you find, let me highlight it. The moment you find this, You're done. You just plug the right, the end, minus the start. And it gives you, so we have 1/2, what is the formula? 1/2,
3 squared, 4 squared.
yes, times 3 squared, 4 squared, minus 1/2, 1 squared, and 2 squared, like so. And it gives you 70. Super simple. And that is the idea, that it makes something complicated so simple. And that's why it's called fundamental theorem of calculus. In this case, it's in 3D. And it's also a line integral. So it's connecting 3 topics in one in calculus 3 class. Yes?
So wait, how did you find out that 1/2 x squared?
Yeah, 1/2 x squared, that's the good question. How to figure this out. So, Sagar, do you want to explain how did you figure it out?
I just did the integration of one of the,
Yeah.
like, for x, y squared, I just did the integration for that, and then just manipulated the square roots and like the coefficients.
Yeah, I also do the same. I choose one, and I'm thinking integral of what could give me x squared y squared in terms of dx, right? Oh no, vice versa. Integral of x y squared dx. In terms of x, it will be, in terms of x, it will be x squared over 2y squared, right? And this is what this part immediately showed up over here. But then 1/2 was like, oh, 1/2 actually also showed up. So I like, wait a second, let me check with the another function. I will check the other function. Integral of x squared y, but with respect to y. Because remember, this one is with respect to y, and this one is with respect to x. Is with respect to y, it is x squared y squared over 2. And it matched. So in this case, actually, it was simple. You will have harder examples in your homework. And that's how you get this function.
Thanks.
You're welcome. Yes?
So you said we can only find the gradient or whatever if we know that f is conservative, but how do we know f is?
Oh, that's an amazing question. Navi is asking, how do we know if it's even conservative? We're going to give you an amazing formula called Green's theorem, which going to go, it's the last chapter of the exam 3. Green's theorem, you will love it though. It will be the best problem in the exam, is Green theorem. So the Green theorem will explain you how to check that field is conservative, and you even have rights to find its antiderivative. What if you spend 3 days finding it? It doesn't even exist because it's not conservative. So that will be an interesting idea to discuss. And one more interesting idea to discuss, why direction matters. It says any curve, so it means I can even go like this, or like this. Can I go backwards? And that's what we're going to cover on Wednesday. When direction matters, when it doesn't, and when choice of the curve matters, and when it doesn't, and why. That is also pretty creative. Mathematics becoming more creative, but then it means it's more challenging. So, good job, and keep doing your homework. Yes, let me stop the recording. Good job, people. I think that's good enough for today. I can feel from the air it was confusing.